All right, so today we're diving into quantum mechanics. And not just any old textbook explanation. No, no. We're going straight to the source.
Straight to the mind of Werner Heisenberg.
Exactly. Nobel Prize winner, one of the founders of quantum mechanics, the whole shebang.
It's like getting a backstage pass to a scientific revolution.
Right. We're talking about his own Nobel Lecture on his groundbreaking work. What better way to understand this mind-bending stuff than going directly to the source?
Absolutely. And Heisenberg, he doesn't just throw you into the deep end with equations. He sets the stage. He walks you through how these ideas came about.
Yeah, and he reminds us that quantum mechanics, this wasn't some overnight paradigm shift. It emerged from this, like, bubbling cauldron of puzzles that classical physics just couldn't handle.
Puzzles, more like gaping holes in our understanding.
Okay, fair enough. So what was one of these major head-scratchers that got the ball rolling?
Well, there were a few, but one of the biggies was something called blackbody radiation.
Blackbody radiation. All right, I'm biting. What is that?
So imagine heating up a piece of metal, right? Like in a blacksmith's forge or something.
Okay, got it.
Now, classical physics, it predicted that as this metal got hotter and hotter, it would emit an ever-increasing amount of high-frequency light. Basically, an ultraviolet catastrophe.
An ultraviolet catastrophe. Sounds intense.
It would be. It'd be like if classical physics were right, every time you heated something up, it would eventually fry your eyeballs with high-energy light waves.
Ouch. I'm guessing that's not what they saw in the lab, though.
Not even close. Instead, experiments showed that the emitted light, it peaked at a specific frequency depending on the temperature. It's like the metal was saying, nope, I'm only giving off this much energy at a time, no more.
And that completely contradicted everything classical physics predicted, right?
Totally. So physicists were left scratching their heads like, what's going on here? Why isn't the metal unleashing this crazy amount of energy?
Yeah, that's a real head-scratcher.
Yeah.
So how did they even begin to explain that?
Well, that's where Max Planck comes in. He's like, hold on a minute, maybe energy isn't this continuous thing we've always assumed.
Wait, what? You mean it's not like a smooth flow?
Exactly. Planck proposed this radical idea. Maybe energy comes in these tiny, discrete packets, quanta. It was a wild thought, like saying you can't pour water in a smooth stream. It has to come out in individual droplets.
Okay, so energy is chunky, but how does that explain the light coming off our heated metal?
Think of it like this. The metal atoms, they can only vibrate at certain frequencies, right?
Okay, I can visualize that, yeah.
And each of those vibrations, it corresponds to a specific energy level, a specific amount of chunky energy. When an atom jumps down to a lower energy level, it releases a quantum of light, a photon, with a frequency directly related to that energy difference.
So the energy of the emitted light, quantized, limited to those specific values because of those atomic jumps. That's wild.
And that was just the beginning of the weirdness.
Well, there's more.
Oh yeah, buckle up. Then Einstein comes along and says, hey, if energy is a particle, maybe light itself, which we thought was a wave, can also act like a particle.
Whoa, wait a minute. So now light is playing both sides.
You got it. Suddenly, this neat division between waves and particles starts to get really blurry.
Right, like light isn't just one or the other. It has this dual nature depending on how you look at it. That must have really thrown a wrench into things.
Oh, absolutely. And it paved the way for even more radical ideas. Like, take Niels Bohr, for instance. He takes this whole quantized energy thing and says, what if it's not just light? What if electrons and atoms are also governed by these quantum rules?
Okay, so remind me, how did we picture atoms back then?
Well, you've got the nucleus in the center, right? And we thought electrons were just zipping around it like planets orbiting the sun.
Right, the classic solar system model.
Exactly. But Bohr, he comes along and says, nope, not quite. He proposes that electrons, they can't just exist anywhere around the nucleus. They're restricted to specific energy levels like orbits, but with a quantum twist.
So instead of orbiting smoothly like planets, they're making these, quantum leaps between energy levels. So it's like these electrons have only certain allowed energy levels, like rungs on a ladder, and they can jump between them, but they can't be in between.
Exactly. No hanging out between the rungs, just these instantaneous quantum leaps.
Wild. But okay, so these quantum rules, they're explaining blackbody radiation, they're explaining atomic structure, but it still feels like we're missing a piece of the puzzle. Like, why were these rules so mysterious?
You're right. It's like they had the answers but didn't know the question. And Heisenberg, in his lecture, he zeroes in on what was maybe the biggest question of all. How do you actually observe something as tiny and elusive as an electron in an atom.
Right, because in our everyday world, seeing something is so simple. You just shine some light on it and boom, you see it. But Heisenberg, he realized that at the atomic level, it's not that simple.
Not simple at all. It's like imagine trying to figure out the position of a soap bubble floating in the wind.
Okay, I can picture that going.
Now imagine you can only observe it by firing tennis balls at it.
Oh boy, yeah, that's going to cause some problems.
You might get a sense of where the bubble is, but you're also going to completely change its motion in the process.
Right, you're going to blast that bubble right out of the sky.
Exactly. And that's the problem Heisenberg ran into. He realized that the very act of observing something at the atomic level, it inevitably disturbs what you're trying to observe.
Because even light, even a single photon, it carries energy and momentum, right?
Absolutely. So when you bounce a photon off an electron to try and see it, you're giving that electron a little kick, changing its momentum in the process.
So the more accurately you try to measure the electron's position, the less you know about how fast it was going or in what direction.
Exactly. And Heisenberg showed that this wasn't just a technological limitation, it was a fundamental limit, like a cosmic speed bump built into the very fabric of the universe.
And that's where his famous uncertainty principle comes in.
Right. It's not just about our measurements being imprecise. It's that at this scale, reality itself becomes inherently fuzzy.
Okay, so it's not just that our instruments are too crude or that we need a better microscope. It's that there's a fundamental trade-off here. Like the universe is saying, you can know this or that, but not both with perfect clarity.
Precisely. And that was a radical departure from classical physics, where the assumption was, hey, in principle, if we just had better tools, we could measure things with infinite precision.
But Heisenberg showed that at the quantum level, that's just not how it works.
Not even close. And what's even more wild, that inherent fuzziness, it's actually essential. It's not just about the limits of our knowledge. It's woven into the very nature of reality at the quantum level. And this fuzziness, it opens the door to this other mind-blowing idea that Heisenberg mentions, Schrödinger's wave mechanics.
Right. Heisenberg's lecture isn't just about his own work. He's weaving together all these other big ideas that were swirling around at the time. So, wave mechanics, what's the gist?
Well, Schrödinger, he takes this idea of light acting like both a wave and a particle, and he flips it around. He says, hey, what if electrons, which we thought were particles, also act like waves?
Hold on, you're blowing my mind here. So now we've got electrons, not as these tiny billiard balls whizzing around the atom, but as, what, smeared out waves?
Yeah.
I'm struggling to wrap my head around that image.
It's definitely a head-scratcher, but Schrödinger, he developed a mathematical equation to describe these matter waves, and here's the thing. The solutions to his equation, they don't tell you exactly where an electron is. They give you a probability of finding it in a certain region of space.
Probability. So it's not that the electron has a definite location, it's more like this cloud of possibilities. So instead of knowing exactly where an electron is, we've got this probability wave, this fuzzy cloud that tells us where it's likely to be.
Exactly. It's like instead of a map with a single dot saying the electron is here, we've got a weather map showing areas of high and low probability, regions where the electron is more or less likely to be found.
Okay, so that's wave mechanics. But then Heisenberg brings up this other big idea, Bohr's principle of complementarity. And how does that fit in with all this fuzziness and probability?
Right. So complementarity, that's where things get really interesting. It's this idea that certain pairs of properties, like an electron's position and its momentum, they're fundamentally linked.
Linked, like two sides of the same quantum coin.
I like that. Yeah, like you can't know both sides with perfect accuracy at the same time. The more you try to pin down one, the fuzzier the other one gets.
It's like a cosmic balancing act.
Exactly.
Yeah.
And Heisenberg gives some really cool examples in his lecture. He talks about how, like, trying to precisely nail down the energy of a system, it puts a limit on how well you can describe how it changes in space and time.
Oh, I see. So it's like if you focus all your attention on one aspect of something, you lose sight of the other.
Yeah. Or he talks about how if you're laser focused on the precise motions of electrons within a molecule, it becomes harder to understand the molecule's overall chemical properties.
Okay, that makes sense. It's like trying to listen to a symphony while also trying to dissect the individual notes of each instrument, you know? Exactly. You can't fully grasp both the whole and the parts at the same time.
So we've gone from blackbody radiation to chunky energy to fuzzy electrons to probability waves and complementarity. It's been quite a journey through the quantum landscape.
It's a real trip, right?
Yeah.
But here's the question. How does all of this connect back to the world we experience every day? How does any of this quantum weirdness relate to our big macroscopic world?
That is the million-dollar question.
Well, Heisenberg actually addresses that very question in his lecture. He uses this really cool example, crystallization.
Crystallization, like how snowflakes form, those intricate symmetrical patterns.
Exactly. So we often think of crystallization as this very ordered, predictable process, right? Like those six-sided snowflakes. Each one is unique, but they all share that same underlying symmetry.
Right, so where's the quantum weirdness in that? Well, quantum mechanics helps us understand the forces that make those atoms come together in those precise patterns. But here's the thing. The exact shape of a snowflake or any crystal, it also depends on chance, on these tiny random fluctuations at the quantum level.
So you're saying there's this element of quantum randomness baked into even something as seemingly ordered as a crystal.
Absolutely. It's those tiny quantum events, amplified as the crystal grows, that lead to the incredible diversity and uniqueness of those macroscopic forms.
So even in something as seemingly deterministic as a crystal, we see the echoes of this quantum fuzziness. It's mind-blowing.
It really is. And it shows us that the quantum world isn't some isolated, esoteric thing. It's the foundation upon which our everyday reality is built.
It really makes you wonder how much of our world, our experiences, are shaped by these invisible, unpredictable events at the quantum level. It's definitely something to ponder.
It certainly is. And maybe that's the most important thing we can take away from Heisenberg's lecture. The universe is far stranger and more fundamentally uncertain than we ever imagined, and that's a good thing. There's always more to discover.
Absolutely. If this deep dive has taught us anything, it's that the more we learn about quantum mechanics, the more we realize how much more there is to learn. So keep that curiosity alive, keep asking those big questions, and we'll catch you in our next deep dive.